So if we validate genomic prediction, well, why do we do that? GBVs, genomic breeding values, are estimated and then used for selection decisions, right? So we need to trust them in a way. They need to be reliable. So if we validate genomic predictions, there's a couple of parameters that we're interested in. Typically, probably the most important is the accuracy of the breeding values, or you could say this is a measure of precision. And here we look at, well, the theoretical definition of the accuracy is it's the correlation between the estimated breeding value and the true breeding value. And higher values there, so values are between 0 and 1, and higher is better. But the problem is we don't know the true breeding value. So that's one. The other thing we're interested is in the dispersion or dispersion bias of the genomic estimated breeding values. And that says something about the scale or the spread of the breeding values. So sometimes we see there's too much variance in those breeding values. And that can be a problem because we typically, people select the best individuals. So if there's too much variance in the breeding values and you select the ones with the highest breeding values, then on average, you're going to overestimate the breeding values of these best animals. And if you're only interested to select individuals within one cohort, it's probably not a problem because you're still selecting the best animals. But if you do it in cohorts with different amounts of information, and some of them are overestimated and other ones are not, then in the end, you're not making the best possible selection decision. So the idea is that we would regress the true breeding values on the estimated ones. And if there's no dispersion bias, the coefficient of this regression is 1. So we need true breeding values, but the true breeding values are unknown. If we knew them, we wouldn't have to talk about this, right? So how do we then validate our genomic breeding values? So what we do is we employ some validation strategy where we mask the phenotypes of a part of the individuals, and then we try to predict them. So if we have a full population, this could be our reference population that we have genotypes, phenotypes, and then we split this population in at least 2, so it can be multiple partitions, and then part of the split is used for training the data, the models, where we use the phenotypes and the genotypes. And the other part, we only use the genotypes and try to predict their breeding values or phenotypes using the inferences from the training population. So we call this training population and reference population. It's the same thing. And then we predict the breeding values for the young individuals. And we compare that to their observed phenotypes that we didn't use in this analysis, right? So if we do that, we correlate the estimated breeding values of these validation animals to their phenotypes. That is not the same as correlating them to the true breeding value, right? These phenotypes, they hold more variance than true breeding values would. And to correct for that, we would here divide by the square root of the heritability of the trait, and that should bring them to the scale of accuracies of breeding values. That's what the theory tells. If we're interested in the dispersion or the scale of the breeding values, so what we would do here is we would not regress breeding values because we don't have them, but we regress phenotypes on the estimated breeding values, and then actually the regression of that, or the coefficient of that regression should also have a value of 1 if the breeding values are unbiased in terms of their dispersion. So, right, so that's what I just said. Yeah, so we estimate these to be properties of breeding values, so that's why we divide by the square root of the heritability, and that aligns with in models using a ratio of variances or breeding values that includes the heritability as well. So all of this is in line with each other, that we are mimicking the correlation of breeding values and thus of breeding values. So what we do here for simplicity, we compute an accuracy, which is just a correlation between the observed phenotypes and the predicted ones. And the dispersion, well, there's no adjustment that's needed there in any case. Right. So in principle, the accuracy that we're computing here today is mimicking the prediction of phenotypes, also the accuracy of predicting phenotypes. Of course, if you compare different models or different methods, and you do this correlation for each method, but then you divide all these correlations by the same value, the ranking of your methods is not going to change because of that. So if we now look at the all the different models that you've been running the variance component analysis for, the interpretation of the predictions, well, it depends on how the models are being parameterized, right? So we have these covariances explicitly modeled in the core block, and then we also try to make these random effects independent in the GMC block. So, but then the funny thing is that for these different models, what we get, like for this core block, we actually get a variance and a prediction that's associated with the covariance. So when I was thinking about this, what does it mean that there's a random effect that is related to the covariance between two different terms? I find it really hard to actually picture this and what to do with this term. But I think it's just another term that helps to predict the variance of the phenotype. So we just should add this back to the phenotype predictions. And that's also done what I've done in the script. And the same for the interaction term, but that's actually, I think, easier to understand. Because we're in animal breeding, we're used to fitting interaction terms and having estimates for those, but not for covariance. So then what's there now for you to do is the fifth part of the exercise, and that implements cross-validation. So I presume most of you know what cross-validation is, but what we do here is we do fourfold cross-validation. So we split the 96 for individuals in 4 equal chunks. And then we run for each model 4 different analyses where, let's say, the groups 1 to 3 are first used as training to predict 4. Then we use 1, 2, and 4 to predict 3, 1, 3, and 4 to predict 2, and 2, 3, and 4 to predict 1. Right. So every time we use 3/4 of the data to predict the other quarter. So we need to run each model 4 times. The code has implemented this, and basically what it means is that if your all the data is used every time, but the fault that you're predicting, the phenotypes are just put to missing values, so they don't come into play. So that's what the code does. It implements this, it stores the predictions, and then it evaluates those predictions. So that's happening at the very end, and that's actually the formal validation step. So there the accuracies are computed, but also the regression for the dispersion bias. Then if you're running this, you may want to fix this first. Around line 455, for the GMI block or the G by M block, the interaction there in the line that states model parameter 5. At the very end, it says K is equal to I, but it should be K is equal to I J K. Just to make sure it's using the correct matrix. Okay, any questions about this part? Yes.
Why number of the groups for classification?
Yeah, so that's a very good question. In this case, I was typically people do something like 5-fold cross-validation, which doesn't have a very good basis to do this or anything. But we had 96 individuals, which is divisible by 4. So that was my reasoning in this case. What you try to do is, I mean, what you also can do is something called leave-one-out cross-validation, right? So you use 95 individuals to predict 1, but then you do 96 analyses. So it's sort of, you want to every time have a sufficiently large reference population or training data to predict the other ones. At the same time, you also want to reduce the total computational burden. So it's a bit of a trade-off between these things. So if you have a large data set, it really doesn't matter too much, right? If you have 10,000 animals, whether you use 8,000 to predict 2 or 7.5 to predict 2.5.
So what if you have, for instance, 500? Because in my experiences, when I performed leave-one-out cross-validation, the accuracies were much larger than when I performed cohort, for instance, 5.
Yeah. So actually, this random cross-validation that we are doing here is maybe not the best approach. I think if you reason from a breeding program, it's good that your validation tries to reflect what you do in the breeding program, right? So in a breeding program, you have your reference population that are somewhat older animals, and with that information, you predict younger animals. So if you have that in mind, it would make sense to say this is the data that we have. We have all the phenotypes and the genotypes, and we sort them by age, and then we just take the youngest cohort, we mask their phenotypes, and we predict them using the other ones. That would really reflect what's happening in practice. So the accuracy that you get is probably also a better reflection of what you may expect in practice. If you do it at random, depending on the structure of the data, let's say if you have large full set families, and you just split them at random, then the individuals that you're predicting, you're masking their phenotypes, but they may have full sets in the other cross-validation forms, right? And they are very useful to predict these individuals that you've masked. But if in your breeding program you don't have full set information to predict your young animals, then this is not reflecting what you see in practice, right? So if you do leave-one-out cross-validation, you maximize this possibility of having all sorts of family information, even from the same generation of cohort, that helps to predict what you'll find. Yeah. So here it was just practical to do it. In reality, in breeding programs, I would advise against using cross-validation. Yes. And if you can't really do it time-wise, what we've done sometimes is we try to identify groups of individuals that amongst them are more closely related, but between those groups they have lower relationships. And then we put the more closely related in the same cohorts and do the cross-validation across those cohorts. Something like that, yes, yeah. Or if you think about, if you have, like in a cattle where you have sires that have multiple offspring, you can just split them by the sire of the, if it's all females, just split by the sire. All offspring of one sire go in one group. Okay, other questions? If not, then you can proceed with running part 5. After that, there's not a part 6. There's no code available, but given based on all the outcome and all the predictions, you can just dig a bit deeper yourself into that. So